Our topic is about the use of disease risk score in pharmacoepidemiologic studies. Firstly, we are going to talk about the motivation to use disease risk score methods in pharmacoepidemiologic studies. Nowadays, automated databases are increasingly used in pharmacoepidemiologic studies. These databases include records of prescribed medications and encounters with medical care providers from which one can construct very detailed surrogate measures for both drug exposure and covariates that are potential confounders. Often it is possible to track day-by-day changes in these variables. However, while this information is often critical for study success, its volume can pose challenges for statistical analysis. Here is a hypothetical motivating example, based on our studies of nonsteroidal anti-inflammatory drugs and cardiovascular disease. It assumes a cohort study of NSAIDs and cardiovascular disease performed in an automated database, with both an exposure and covariates that can change on a daily basis throughout follow-up. From this example, we can see three main challenges. The first is computational complexity. Even with modern computing capacity, models with 80 time-dependent covariates will require substantial computing power, and analyses may be cumbersome, particularly if there are dependencies that require more complex variance estimation. Second is the question of model specification. Many of the risk factors for cardiovascular disease confer relatively modest increases in disease probability. Variable selection procedures may exclude important covariates from the final model. Furthermore, techniques for constructing parsimonious models, such as stepwise regression, have limitations that can lead to underestimation of standard errors for exposure estimates. The third challenge is the question of effect modification. Clinicians are interested in whether or not the risk conferred by an NSAID varies according to baseline cardiovascular risk status. However, with 50 variables that measure this factor, the effect modification analyses may be cumbersome. One common approach is the use of propensity scores. An alternative approach is to construct a disease risk score. There are 3 steps to calculate a disease risk score. First step is to select an appropriate model linking the exposure and covariates to the outcome. For example, what we often use are logistic regression, binomial regression, Poisson regression, proportional hazards. This is then used to fit a model in the unexposed group from which one can estimate the probability of disease occurrence. Finally, we calculate the estimated probability for each cohort member under the assumption of no exposure, and it is the estimated disease risk score. This method was originally proposed by Miettinen in 1976, to permit controlling for confounding variables using simple stratified analyses. The rationale for disease risk scores parallels that for propensity scores. We consider a cohort study with fixed follow-up and a binary disease outcome in which the objective is to determine the effect of an exposure on disease occurrence probability. Further assume that for the entire cohort, probability of D given E plus equals to gamma multiply probability of D given E minus, where E plus, E minus denote the presence and absence of the exposure and gamma is the risk ratio. If, given E minus, the disease occurrence probability is a known function of the covariates, then from this one could calculate the disease occurrence probability for each cohort member, given E-. These known probabilities in turn could be used in various ways to derive unconfounded estimates of the risk ratio. This method was examined by Pike and his colleagues, and they concluded after studies that disease risk score defined by Miettinen would exaggerate the statistical significance of the measure of effect for exposure of interest. And it was later re-examined by Cook and Goldman. They found out that the overstatement of significance levels have material impact only in a relatively extreme circumstances. That is when the squared multiple correlation coefficient between exposure and confounders exceeded 90%. As we just mentioned, propensity score is also a common approach for these studies. Let us put propensity score and disease risk score together, and make a comparison to see how well they perform in different scenarios. What is propensity score? The most common option consists of 3 steps. First step is to match E+ and E subjects according to propensity score. Next, assure balance in the distribution of covariates between 2 groups. Then, we weight each observation by the propensity score or perform an analysis stratified by the propensity score, one circumstance in which propensity scores are clearly superior to disease risk scores. For example, consider the NSAID scenario, but with the outcome a disease for which fewer than 50 cases were expected. Then the model necessary to calculate the disease risk score could not be fit, whereas that for propensity scores could. However, in reverse circumstances, assume one of the NSAID exposures is high dose of a CUHK, and fewer than 50 exposures are expected within the cohort. Then, even if the outcome probability was relatively high, for example it is 0.1, propensity scores could not be calculated, whereas disease risk scores could. In pharmacoepidemiologic studies, we see that not all cohort members obtain medications with a prescription, so-called over-the-counter, while the automated databases employed by studies typically are restricted to prescribed drugs. In this case, use of propensity scores may increase the bias due to misclassification. Inclusion of variables strongly associated with the exposure in calculating propensity scores may preferentially identify apparently unexposed subjects who are misclassified. However, disease risk score is less affected by this phenomenon, since these variables only influence it if they are also associated with the outcome. In case control studies, people find that propensity score methods perform even worse than in cohort studies. Propensity score methods either introduce artifactual effect modification or bias in estimating the odds ratio, while there are no obvious problems with using the disease risk score. Another common question in pharmacoepidemiologic studies is whether the risk conferred by a drug varies according to baseline risk for the outcome under study. The disease risk score provides a natural way to test for this type of effect modification. However, the propensity score does not measure disease risk and thus cannot be used in this manner. Indeed, because the propensity score may not have an obvious medical interpretation, the clinical relevance of analyses stratified by propensity score is uncertain. Next, we are going to illustrate simulation studies comparing regression models using the disease risk score to conventional models. In primary simulations, we generated a binary, non-time dependent exposure, a binary disease outcome, a fixed period of follow-up with no censoring, and 30 confounders including both binary and continuous variables. We considered event probabilities of 0.1 and 0.01 and exposure probabilities of 0.1, 0.01 and 0.001. For each simulation setting, we generated 1,000 samples, with each sample consisting of 10,000 study subjects. To evaluate the two methods, we compared the percent bias, empirical power and coverage probabilities, the proportion of 95% confidence intervals that included the true regression coefficient. We also compared the standard error, SE, of the estimated regression coefficient for the exposure to the standard error estimate, SEE, which is the standard deviation of the estimated regression coefficients from the simulated samples. The mean SE should approximate the C. We get the result that the mean SEs approximated the C well. The SEs and Cs from the risk score models were similar to the corresponding mean SEs and Cs from the conventional models, although in some settings were slightly smaller. Bias, coverage probabilities and power were similar between risk score and conventional models. However, the primary simulations, which reflected the underlying pharmacoepidemiologic examples, had moderate correlation between the exposure and confounders. We thus conducted additional simulations that assessed the effect of more extreme correlations. We simplified our investigation and considered 10 binary confounders. We induced correlation between the exposure and the confounders as follows. First, we selected 3 confounders and set the prevalence of these confounders to 0.1 in the unexposed group. For the exposed group, confounder prevalences were 0.1, that is no correlation between exposure and confounder and thus no confounding, 0.2, 0.5, 0.7 and 0.9. The event probability was 0.01 and the odds ratio for the exposure 2.0. Figure 1 summarizes our findings for this scenario. When the exposure and confounders were independent, the disease risk score and conventional models had similar results. For moderate degrees of correlation that confounder prevalence in exposed group no more than twice that of unexposed, performance of the disease risk score was quite comparable to that of the conventional method. However, for extreme differences between the confounder prevalences in the exposed and unexposed groups, the relative performance of the disease risk score deteriorated materially, both in terms of coverage probabilities and bias. We also considered a model misspecification scenario that is likely to occur in pharmacoepidemiologic studies in which there are many covariates, each of which confers only a moderate increase in the probability of disease occurrence. In this simulation, we assumed 10 binary covariates each with an odds ratio of 1.2 and others same as before. Figure 2 summarizes that in this case the disease risk score performed better than the conventional analysis, even though performance of the former deteriorated for high correlations between exposure and confounders. Here we use SAS to run the simulation and the simulation code and results are included in the attached files. Now we are to talk about some new applications. For first new application, in fact we can try to use propensity scores to predict the life satisfaction by the cultural activities engagement. In the statistical analysis of observational data, propensity score matching is a statistical matching technique that attempts to estimate the effect of a treatment, policy, or other intervention by accounting for the covariates that predict receiving the treatment. We can apply it to the change of life satisfaction by regressing the categorical variables of different types of cultural activities that the citizens engaged. It is in fact quite useful for policy making, especially for Hong Kong. For the second new application, we can try to use the concept of disease risk score to predict the likelihood of landslide. There are a lot of factors determining the safety of soil, but they are not exposed and very often we cannot sense them. By defining a risk score can help us know more about the presence of landslide. It is also quite useful in Hong Kong context. Here comes the sixth section, the improvement of our research. First of all, in order to improve the result, we can randomly resample the data. We randomly resample the 10,000, 1,500 persons by 1,000 times. The benefits of it is it provide the equal chances of every data being chosen. Here comes the VBA code that we have done. The second improvement of the result, we can use LaSue for the convex optimization of the disease risk score. LaSue is the popular model selection and shrinkage estimation method. Even if the number of predictors is much larger than the sample size, the group LaSue estimator is still statistically consistent, getting rid of the problem of the deterioration of the common logistic regression. Further optimization can be done on the LaSue estimator and thus the robust model can be obtained writing a for loop. PCA will also be A+ in reducing the dimension of the problems. The advantage of LaSue is in fact solving the high-dimension disease risk score problem. Usually in high dimension, the modeling of risk score will be overfitting and have poor performance. But with LaSue and PCA, we can simplify the problem and get a more accurate result. Here comes the logistic group LaSue algorithm using block coordinate descent minimization. Here comes also the logistic group LaSue algorithm using block coordinate gradient descent minimization. For the third improvement we can think of, it is the k-means clustering. As the data used in the research paper are without group information, we do not even know how many groups exist in the dataset. We need k-means clustering as the unsupervised learning strategy. Of course, it will be the best if we could obtain the group information of the population investigated. We can further apply stratified sampling technique to ensure the unbiasedness of the result. Here comes the algorithm for k-means clustering. Last but not least, they are the references.